All right, I guess it's time. It's my pleasure to introduce our next speaker for today, Kirk McDermott, who will be talking about topological aspects of the shift dynamics for the groups of Fibonacci type. Thanks, Kirk.
All right, thanks, Molly. Thanks to you and the organizers and for everybody coming here to listen. I appreciate it. Right, so to begin, let me define what's called a cyclically presented group. We begin with a free group on N generators. And today we'll be talking a lot about the shift automorphism, where what we'll do is we'll cyclically permute the generators. And so when you get to the n-1 generator, you're back to the 0 generator. So we'll just treat subscripts not n. And then in order to build the groups, we'll take a presentation by taking any word in the free group. And here is our cyclic presentation now. So you've got your n generators, and then you've got your relation word W, as well as all of its shifts. So we'll call this a cyclic presentation, and I'll stick to cursive letters for the cyclic presentations. And then for regular letters, we'll refer to those as the groups given by the presentation. So what people do in this area is investigate infinite families of group presentations. And what you want to do is, given some infinite family of presentations, determine first solve the finiteness problem. Could you figure out which groups are finite? Also very popular is, given a family of cyclic presentations, determine which are spherical. What's meant by that is for any presentation, there's the presentation complex, the two-dimensional CW complex, and say spherical if it's second homotopy group trivial. You could also say contractible universal cover. It turns out cyclic presentations arise a lot in three-manifold topology. So another popular problem is, given some infinite family, determine which of these cyclically presented groups are three-manifold groups. Or, as is often the case, the presentation themselves might be the spine or even the two-skeleton of a three-manifold. Finally, they tend to have interesting first homologies. So people like to calculate the abelianizations of these groups. Some examples here to begin. First, the Fibonacci groups. Here, the relation is x0 times x1 times x2 inverse. It's considered a Fibonacci relation because you're saying there that the product of x0 times x1 equals x2. So that's the Fibonacci spirit there. And again, what these cyclic presentations do is they shift each relation. So notice each index gets shifted up one to form your next relation. And then by the time you get to the nth relation here, if you were to shift it up one more time, you'd be looking at x0, x1, x2 inverse, so you'd be back where you started. So again, these are all balanced presentations. Cyclic presentations have been investigated, I mean, really since the beginning of group presentations themselves. But what people usually refer to as the first citation is Conway, who in '65 posed a MAA problem in a monthly, saying to prove F2 here, so take n equals 5, and prove it's isomorphic to the cyclic group of order 11. And the reason people use that as the first citation is because tons of people responded. And I mean, in hindsight, it's pretty interesting too, because some really famous group theorists were responding to an MAA problem. I doubt that's the case anymore, but maybe it is. Anyways, all these people responded, and immediately people were like, what happens if n is 6 or 7, and so on and so forth. And so right away, people were looking at this infinite family now, depending on n. And you can see my 2 here. You can imagine how people might generalize things as well. So the finiteness problem was the first consideration here for these groups. Turned out it's finite if and only if n is 1 through 5 or 7. Interestingly, it's infinite if n is 6. And it's surprisingly hard. Check it out. Look at this. It started off in '65, and right away, people figured out most of them, which were infinite. But it wasn't until 1990 that the last one, F29, was sorted out to be infinite. And what's happening here is these are all undecidable problems. So what's happening here is eventually computers became fast enough to implement certain algorithms, and specifically it was a coset enumeration, and in that way they were able to figure out the last one was infinite. Okay, but what about the topology? Well, it turns out if n is even, then these cyclic presentations are the spine of three manifolds. And so again, one of the popular problems here is the asphericity problem. And if a presentation is not a spherical, that means there exists an essential spherical map. So a spherical Vancamping diagram. And it turns out what you can do is treat these spherical Vancamping diagrams as a tessellation of the boundary of a three ball. And you can then do a face pairing construction. And so what these people are doing here, Helen, Kim, and Menike, is they take this essential spherical map into the cellular model. They perform a face pairing construction and prove that it's the spine and in fact two skeleton of a three manifold. And they also show it's hyperbolic or m greater or equal to 4. And people like these sorts of things, and people were looking at it, and some knot theorists looked at it right away and realized these manifolds were homeomorphic to the M fold. So notice there's 2 M generators, but it's the M fold cyclic branch covering of the figure 8. And the dates look like I've got a typo there, but there's just some delays in publication. All right, so just one more example here, the Spherical groups. These were introduced by Spherical in '86, and these were introduced directly as spines of 3 manifolds. Again, through the same process, beginning with essential spherical map into the model. You can think about it as the boundary of the 3 ball. You perform the face pairing. Finiteness problem. This time it turns out there's no gap in the integers, so just n less or equal to 5, you're finite. And around the same time, people were thinking about the M-fold cyclic coverings of those Fibonacci groups. People want to know what was going on here, and it turns out these manifolds are homeomorphic to the N-fold cyclic branch coverings of the trefoil knot. And interestingly here, all we're doing is going from X1, we're going from X naught, X1, X2 inverse to X naught, X2, X1 inverse. And mysteriously, we get manifolds in every case, and these are all cyclic. Finally, once you know that they're cyclic branch coverings of the trefoil knot, I mean, that construction on its own was investigated much earlier on. And these turn out to have periodic first homology. All right, so today I'd like to talk about the shift dynamics of these groups. So again, the shift is the defining homomorphism of the free group, well, automorphism, which is cyclically per median of generators. And it hasn't received a lot of attention in the literature. Some problems are as follows. Determine the order of the shift. It's got exponent n, but what's its order? Does the shift act freely on any identity elements or any powers of the shift? There's a full Zn action on the group. If there are fixed points, find them. Find the structure of the fixed point subgroup. Finally, this shift determine if it's an outer automorphism. We'll see in a little bit that the fixed points sometimes turn out to be the conjugating element for an inner automorphism. So some motivations, why would you want to study the shift? Well, a classical theorem of Thomson here on finite groups, in this context, it's not about cyclic presentations, but if you direct it to the cyclically presenting groups here, it turns out if the shift action is free and the group's finite, then the group's nilpotent. But the group structure is not known in cases when there's fixed points or if the group's infinite. For the topology, Cavicchioli, Repose, and Spagliari, they consider some presentations, and they're trying to figure out conditions when you obtain hyperbolic logofolds with finite volume. Among the hypotheses is that you need shift to have order n. And here they're generalizing a result of McLaughlin from '95. And finally, Lin and Wang have a theorem, which is a consequence of Moss-Al rigidity, which characterizes all possible fixed point subgroups of an automorphism in cases when that group is the fundamental group of a hyperbolic free manifold of finite volume. And they've got characterizations in a variety of cases, but here we are obtaining closed manifolds, and the shift, it turns out, typically induces an orientation preserving isometry. And in this case, they show that the fixed point subgroups either going to be integers or the group itself. Okay, so I'd like to focus on the following infinite family of cyclic presentations. These are the groups of Fibonacci type. So instead of the Fibonacci group where you had x0, x1, x2 inverse, now allow for any values nk. We're still working with indices mod n, so any values between 0 and n. And these are a really well-studied class of groups. The finiteness problem has been solved, the sphericity problem, and then in the last few years, the three-manifold spine and group problems have been solved. Interestingly, there's two exceptional cases. If you take n equals 9, and then m is 7 and k is 1, I forget the other one off the top of my head. Very little is known about those groups. It is surprising, not for lack of effort. A lot of people would like to know if they're finite, but no one's been able to prove it. Recently, though, they were shown to be not aspherical. So I've been studying the shift dynamics of these groups, and what I found is that the shift has order n in all cases, and it's an outer automorphism if and only if the group's not perfect. So the abelianization is non-trivial. And as the perfect groups were identified, Gerald Williams in 2010 identified them as perfect if and only if you're one of those Spherical groups where the n and 6 are relatively high. In all other cases, the shift's an outer automorphism. So my main tool is asphericity. That's the hypothesis I work with the most. And my PhD advisor, Bill Bogley, he showed in 2014 that if the cyclic presentation is aspherical, then the shift action on the group is free on non-identity elements. And so the way this works then is when you're working with these classes, and here are the, let me back up. When you're working with these classes, there's been many classifications for asphericity. So the way it goes is typically one implies some sort of curvature arguments to determine large groups of, or families rather, of aspherical presentations. And then you've got a list of non-aspherical ones that you need to consider. So anyways, for the aspherical case, you know you've got a free shift action. And if you've got an inner automorphism, the conjugating element's always going to have a fixed point. The element you conjugate by will always be fixed if you conjugate it with itself. So the upshot here is that if you're aspherical, then the free shift action tells you that the shift's outer automorphism of order n. So I'm going to leave this as a black box, but it turns out cyclic presentations, you can form a semi-direct product determined by the shift. You obtain a two-generator, two-relation presentation, which allows you to easily produce a relative presentation. And Martin Edgevet in '94 solved the asphericity problem for all these one-related relative presentations. So we can use this classification and see what's happening in the non-aspherical cases. Let me just give you one example for today. Look at a spherical Vancamping diagram here for the Fibonacci group where n is 6. So this is a spherical Vancamping diagram. I want you to think about this as a tessellation of the two-sphere. And let's see, each relation must appear, each face must be labeled by relation. The oriented edges. General Vancamping diagrams don't have to be spherical, but here the spherical is coming from observing that the outer longitude here and the outer longitude on the right, they have the same labels, so you can imagine folding them together and therefore obtain your two-sphere. And the thing to notice is it's got a rotational symmetry that's a shift equivariant. Notice that if you took, so I've got n and s here, obviously from north-south poles. If you gave that thing a twist, it's the exact same as if you applied the shift twice. So each longitude here differs by a shift of power 2. Passing from x5 to x1 here, we're working mod 6 right now. So it's shift power 2, rotational symmetry. And what I want to notice is the following. There's a longitudinal path here. Now, it's not the easiest path, but it's a commutator. Check it out. If you go north pole down x0 over x1, x0 inverse, x1 inverse. Looking at a commutator there? And you can find its shift twice, x2, x3, x2 inverse, x3 inverse. And so because you've just formed a disk, and this is a spherical map into the presentation complex, I've just argued then that we've got a fixed point of the shift squared. So in detail, those Vancamping diagrams give you a spherical map into the model. You've got a 2 pi over 3 rotation of the 2 sphere. Again, it's got this shift equivariant symmetry. For your presentation complex, the shift naturally induces a homeomorphism on the model. Just rotate the bouquet of circles in the relations, and they commute as follows. And then this polar path, again, it's shift fixed point of the shift squared. And I'm not going to show today that how it's non-trivial. That's a funny typo, non-trivial. But anyways, I'm not going to show today how it's non-trivial. But anyways, I picked that path because you want to work in the optimization to reduce that. So what's the upshot here? Well, I mentioned the result of Lin and Wang. With that in mind, you can show the shift squared is induced by an orientation preserving isometry. You can argue that the fixed point set is the integers, but at the same time, you can also show the shift is not induced by an orientation preserving isometry, and in fact, it's got no non-trivial fixed points. Remember, that's the hyperbolic case now, those Fibonacci manifolds. In contrast, if you explore what's going on with the Spherical groups, it turns out they're fixing, the shift is fixing a central element of infinite order. And you can see that from a spherical Vancamping diagram. You can also just argue that directly with the presentation. It's not terribly difficult to show that there's that central element. And so what's interesting here is that this having a central element of infinite order that recovers the fact that all these manifolds are ciphered fiber. So let me just conclude by trying to generalize this a little bit. So I solved the fixed point problem for the whole family of groups. For that family of the groups of Fibonacci type, it turns out those are the only 2 infinite families of 3 manifold spines. There's some other 3 manifold groups in there, but they're just finite cyclic. But in these 2 cases with the 3 manifold spines, here's my attempt to try to generalize what's going on. And it turns out that central element plays a key role in what's going on. So if that group here, now in general, now not just the Fibonacci type, any word W in the free group, if it's got order n and you're torsion free and centerless, then the shift has order n in the outer automorphism. And it's actually not too hard to show. If some power of the shift were an inner automorphism, then there'd be a conjugating element. So say theta to the p is GHG inverse for all H. Now the first equality here follows because that shift has exponent n. So you could say that equals p times n divided by the GCD of n and p. And as a result, then your conjugating element to be n over that GCD equals H. So if you write multiply, then you've just learned that G to the n divided by n over P is a central element and possibly trivial. So again, the lemma then is that if you're torsion free and centerless, then the shift must have order n in the outer automorphism. Now this does apply back to the topology. So if you're the fundamental group of a hyperbolic 3 manifold, like those Fibonacci groups, then the shift must have order n in the outer automorphism group. And I'll be honest, in the spirit of the workshop, I'm not sure if this consequence here is necessarily deep or anything. Maybe that's obvious to some 3 manifold topologists out there, but it is an interesting consequence of this shift dynamics. See how we're doing. I think I'm going to stop here. Thanks for your time, guys. Does anybody have any questions?
Let's go ahead and thank our speaker real quick here. And yeah, are there any questions for our speaker?